Hello and welcome to this Institute of Physics CPD session on everyday forces. My name is Sue Woolhouse and I'm an IOP coach. This is the first in our series of 3 sessions on forces. Please do join us, if you haven't already, for part B on force arrows and part C on balanced forces.
So why do we teach about forces? Well, forces tell a physics story. Forces make things happen. Forces are our friend because having a good understanding of forces enables us to explain all sorts of physical processes in our world. And this is especially important with the new approach to teaching energy. We need forces to help us to describe how energy is shifted between stores. But force is an abstract concept, so let's support students with plenty of explorable examples of forces in action. Now this is the list of types of force from supporting physics teaching on IOP Spark. You might notice slight differences to your own department's force glossary, but what's important is there is consistency across your department and with your exam board. So for example, both Excel and AQA use normal contact rather than compression force at GCSE. So here's the challenge. Can you set up a series of experiments to explore different types of force using the contents of this bowl? It's all about everyday physics. No fancy kit, just things you might already have in your home. And this approach fits really well with the science capital teaching approach, using examples and settings that are familiar to our students as hooks into the science content. Everyday physics also supports some of our top 10 tips for inclusive teaching, and we'll share this link. So increase inclusivity by using examples that show how science links to students' experiences. And this is useful for all students to appreciate context and also see the bigger picture, and use gender neutral context wherever possible, avoiding using examples that focus on stereotypically male or female hobbies or interests. And because we're exploring familiar contexts, it's an opportunity to regularly refer to a range of careers that use science-based skills, and also to emphasise the transferable skills that studying science helps to develop. And it's a chance to ensure the students are exposed to a diverse range of scientists. So be wary of giving students the impression that science is only for high achievers. Emphasise that science is for everyone. This will also support your school's work on the Gatsby Good Career Guidance benchmarks, especially embedding Gatsby Benchmark 4, linking the curriculum to careers. So that's what we'll aim to do this session. Look for ways to use everyday kit to explore the different types of forces and make links to both context and careers. It's amazing how many ideas some seemingly random bits of kit can generate. And I'm sure you've already got lots of ideas buzzing around yourself already. So let's start with looking at the contact forces. Firstly, the ones that oppose motion: grip, slip, and drag. Now, many students will have the misconception that you only get friction when things are moving, but we want them to understand that friction exists between all surfaces moving, slip, and tending to move, grip. And a flip-flop or any shoe enables them to explore this idea. So a flip-flop on a slope, how steep does the slope need to be before the grip is overcome and the flip-flop starts to slide? Is it the same for all flip-flops, or does the size or the tread make a difference? And what happens when you load the flip-flop up with masses? Or try sliding it on a different surface. And to investigate slip, you can attach a Newton meter and pull the flip-flop along a surface at a steady speed and actually measure the force required to make that happen. So there's quick demonstration opportunities, or you can see how you might be able to expand some of these ideas into a bigger investigation for your students. So we can see our shoes give us a really good context for exploring friction, both grip and slip. And then we can get our students thinking about the shoes that they might use for different sports and activities, and what the tread and the design of the shoe looks like depending on what the activity is. And we can think about related jobs. Obviously, a shoe designer thinking about the treads, or what about a material scientist who's designing different materials and thinking about their grip and slip properties? Or how about a sports ground manager getting pitches and grounds in tip-top condition, ready for big sporting events? Now, drag is the other friction force, and we all know that when an object moves through a fluid, a liquid or a gas, that progress is opposed by a drag force. Students have experienced air resistance when they're speeding along on their bikes, or drag when they're swimming through water. And cupcake cases are a great way for investigating air resistance. For example, compare how a crumpled one falls versus an uncrumpled one, or two together versus a single one. Drag forces get greater when things move faster, so this can be investigated by dropping parachutes and thinking about their motion. What about contexts and careers? Well, we've talked about swimming, we've talked about bike riding, but how about if you're a marine biologist thinking about studying streamlining in fish? Or you might be the performance manager of a Tour de France team, and you're working out which cycle helmets are the best ones to invest in. Or you might be a skydiver making the decision when to open her parachute.
So what about the other contact forces, the support forces, buoyancy or upthrust, compression or normal contact, and tension? Well, let's start with buoyancy. Students will have done plenty of floating and sinking experiments in the bath or swimming pool, or even when they're washing up. But it's really good to get them thinking about the forces acting on a floating duck. There's a really nice piece on IOP Spark about how the feathers of diving birds are adapted to reduce their buoyancy so they can dive deeper. And also get students to experience buoyancy by pushing a balloon down into a bucket of water. And they'll really feel the force, the buoyancy force increase as more water is displaced. They might well have done this investigation already when they tried to stand on their float in the swimming pool. What about context and careers for buoyancy? Well, we might want to think about a swimming teacher trying to decide when to remove a child's armbands, or a diver doing underwater repairs on an oil rig, or a submarine commander planning their route, or the captain of a cargo ship deciding on how many containers they can load, or maybe even a party planner filling up helium balloons. Now let's think about compression or normal contact force. And you might already have linked the sponge to compression or normal contact force. And compression forces can be experienced by a balloon, again, pushing the sides of the balloon and feeling the pushback, or indeed compressing that sponge. And here's a quantitative investigation from IOP Spark, and it uses very similar skills to the stretching the spring experiment, but we can actually quantify the amount of compression and plot graphs in a similar way. And there's another example of how a quick demo can be expanded into a larger investigation. How about context and careers for compression? Well, manufacturers of mattresses, sofas and flooring will need to be aware of compression. Car designers need to understand compression forces to make cars safer with well-designed crumple zones. Compression forces are also important to architects and engineers designing bridges and buildings. How about tension? Well, you might have spotted the strawberry laces as a good way to explore tension. And again, it's a good alternative to the traditional Hooke's law experiment. I've seen many people creatively twisting and plaiting the laces to investigate the strawberry laces even further. Fishing elastic is also a good alternative for an investigation because different diameters come in different colours, so that can be really helpful.
And of course, we can also complete the traditional stretching the spring experiment. And there's a version that might be useful to you on PhET. It's a simulation, but it's interactive and you're able to increase the force on the spring and actually take measurements for extension that you can use to plot graphs and look at spring constants. How about context and careers for tension? Well, if you're a health and safety manager, risk assessing a bungee jump, you're going to need to answer lots of questions like how long does the rope need to be? What's the maximum mass for the jumper? What's the spring constant for the elastic? Also, if you're designing a bag for life, how does the bag behave under tension? What's the maximum load it can take? And is that about right for a bag full of shopping? And again, architects and engineers, if they're building a suspension bridge, they'll need to think about tension in order to make sure that that is safe. So finally, we've got the non-contact forces, gravitational, magnetic and electric. Now, these forces all involve fields, an abstract concept for students, so let's give them plenty of opportunities to explore them in action. You've probably noticed that gravitational force is involved in almost all the examples that we've looked at so far: parachutes, ducks, balls, cupcake cases. And when you look at the force arrows in the next training session, then you'll see that gravitational force or weight keeps popping up. What about context and careers? Well, weight on different planets is an interesting context. It's not exactly everyday physics, but it's a chance for students to think about space, which is a great gender-neutral context. Another example of a non-contact force is magnetic force, and these fridge magnets enable you to explore this Marvin and Milo investigation. And magnetic notice board pins are also good for experiencing the force, and also showing the students the paperclip and the magnet trick is another good hook into the ideas. And it's really great if you can get students to really feel the force, to feel the attraction and the repulsive force. I'm cheating a little bit here with these big magnets, but if they can just experience those forces and their non-contact nature, then that's really powerful. In terms of context and careers, well, we can look at a recycling plant separating iron and aluminium cans. We could look at electromagnets used in combine harvesters as a threshing mechanism to reduce mechanical wear and tear. Or if you just look around your school, you'll see electromagnetic door locking mechanisms in different classrooms. Finally then, what have we got left? Well, we've got the cans, some bottle tops, some straws and the balloon again. And this kit enables us to do two of my very favourite Marvin and Milo experiments, which illustrate electrostatic forces beautifully. So we've got this one with the rolling can. And we've got this one with the spinning straws. Charge up 2 straws with a cloth, balance one straw on a bottle top, bring up the second, and you will see some nice repulsion. And bring up your finger and you'll see traction, or the cloth will do the same. What about context and careers? Well, for electrostatics, we've got painting cars, repulsive forces to get a really fine spray of paint droplets, and then attractive forces to ensure that the paint actually sticks to the car. Physics is so useful. What about somebody having to risk assess refueling aircrafts or cars to make sure that they get discharged before the fuel actually flows? So that's it. A washing up bowl full of everyday kit to explore the 9 forces. Hopefully this whiz through everyday physics has given you some new ideas about exploring forces with your students, and also a range of contexts and careers for the forces topic. Thank you for joining us.